Welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to look a little bit more at another building block of electronics, and that's the concept of phase, which is something that certainly crops up with circuits that involve alternating current. So we're going to have a look at what it is, how we can visualize that on an oscilloscope, and we're also going to look at the effect that some types of discrete components can have on phase. Now, in my world, phase is the relationship between two different waveforms, and I guess it's the relationship between them in terms of time. Phase is usually expressed in degrees, 0 degrees being the two waves are in synchro, 180 degrees being they're just about as far apart as you can get, and 360 degrees they're actually back where they started at 0. So what we're going to do is start by having a look at how that appears on the oscilloscope, and we'll do that in two ways. First, in the conventional way using a dual channel scope, but at the same time we're also going to view what happens on the scope that's set into XY mode, as that presents a bit of a different example of how you can view phase. So let's start by looking at the scope. Okay, let's start by having a look how phase appears to us when viewed on the oscilloscope, and I'm going to do that in two ways. On the left hand side you can see the display of my Hameg HM307 analog oscilloscope. It's a single channel scope. I've got it set in XY mode, so I've got one channel fed to X, one channel fed to Y, and on the right hand side of the screen the output from the Siglent scope, and I've got a function generator producing two 1 kilohertz sine waves. As it happens, they're at 4 volts peak to peak, although that's not terribly important right now. And I've got the measurement on the Siglent at the bottom there showing the phase relationship between channels 1 and 2, and it's saying about -1 degree. In reality, the signal generator is currently set at 0 degrees phase. So what I'm going to start doing is I'm going to start increasing the phase between channel 1 and 2. I'm starting to move it now. That's about 10 degrees, that's about 20, approaching 45 degrees, and at that point there, just over 45 degrees, you can see the two traces are beginning to separate. The measurement is saying about 49 degrees out of phase, and you can see that distinctive elliptical shape that's appearing now on the scope in XY mode. I'm going to continue to 90 degrees. That's 85, that's 90 degrees, so we're sort of 1/4 of the way out of phase now, and you can see we've got a vertical, quite tall vertical ellipse on the scope in XY mode. So I'm now going to continue fairly rapidly at 120 degrees there. The ellipse is looking similar to 90 degrees, except it's leaning in the opposite direction. I'm going to keep on going now to 180 degrees, and there's 170. There we go. Yeah, there's 180. So you can now see very distinctly that the two waves are effectively about as far apart as they're going to get, and we've now got a slanting vertical line on the scope in XY mode, slanting from top left to bottom right. If I now continue, I'm going to continue fairly rapidly up to 270 degrees. That's 270 degrees there, and interestingly the measurement on the scope now thinks it's about 90. That's because if you look at the display on the XY mode is identical. We've got the vertical ellipse, and although the purple trace is now 270 degrees behind the yellow trace, the scope is interpreting it as 90. I suspect if I triggered off channel 2 you'd get a different result. I'm going to keep on going now right up to 360, and the effect if I can see the display properly, the effect at 360 is that we're now back to where we started. We've got a sloping line sloping top right to bottom left on the XY mode, and the two waves appear in sync again now. So that's how the phase relationship between two sine waves appears on two oscilloscopes set for two different modes of display. Okay, well, hopefully that's made a bit of sense, and you've seen the difference between two sine waves as they move back, move apart and move back into phase, and you've also seen how that appears on a scope in XY mode. And I suppose one question is, does it matter? Well, the answer is yes, it can matter, but it doesn't always matter. For example, this HX108 little Chinese radio kit that some of you may have watched me build in some previous videos, if I were to swap over the wires that are feeding the loudspeaker, I would effectively be changing the phase by 180 degrees. Would the radio sound any different? Well, no, certainly wouldn't be able to tell. And certainly for a lot of mono things, that probably is the case. If you're working with stereo, things can get a bit more different. Most hi-fi buffs and sound buffs will tell you that if you've got one of your speakers out of phase with the one, instead of them moving in synchro, they're actually moving opposite. There'll be some cancelling out effect. Now obviously we don't listen to things in perfect acoustic spaces, so there's going to be all sorts of other complications going on, reflections, reverb, etc. But generally most hi-fi buffs will tell you that if the speakers are out of phase, it usually manifests itself in a sort of a thinner sounding bass response, which sort of makes sense to me from a scientific point of view, because obviously the lower frequencies are the longer wavelengths, and the human ear is more likely to detect those changes in sound pressure. As the frequencies increase, those wavelengths are a lot shorter, and I guess our ears probably can't keep up quite so well. So let's now have a look at the effect of phase on a particular type of discrete component, the transformer. Let's start by looking at a simple transformer, which effectively isolates two parts of a circuit. And what we're going to do is we're going to feed in a sine wave to left hand side, and hopefully what's going to appear on the other side is a similar looking sine wave. Now it's possible for the voltage relationship to change, but we won't go into the details of that today, but the waveform for the most part should be similar, if not the same. Another possible outcome is to feed the sine wave in as before, but what we actually get is a sine wave that's 180 degrees out of phase, and that could be because of the way the transformer is being wound, but it could also be to do with how we wire it up. Now it doesn't appear a great deal in circuit diagrams, but you may on occasion have seen a pair of black dots, as like so there on the left hand side, and they are to indicate the way the transformer should be wired up, because it matters that the phase remains the same before and after it's passed through the component. Whereas on occasion we actually want the converse to happen, and so you might see something like that, with the dot on the top left on one side and bottom right on the other. Now it doesn't occur on lots of circuit diagrams. I've managed to find this one here, which is an extract from my VEF 204 Russian receiver, and these are a couple of sections of the input and the oscillator stages, which is switched in and out using a sort of a carousel arrangement. You can see a video on that radio. I'll put a link up the top there for you for that. And you can see on the left hand side I've put some red arrows that there are two dots there indicating that transformer needs to be wired in that particular way because the phase is important. And rather handily on the opposite side, actually on the bits that work with the oscillator, you can see that that particular coil is required to be wired such that the phases are at the opposite directions, and there are usually indications on the component to enable you to make sure you have wired this up correctly. Other examples of phase changing, delay circuitry. It's possible to create a phase change. In fact, in some audio applications, recording studios, they make use of a delay to correct for issues with sound response caused by phase issues. And sometimes in certain amplification stages we get a phase change. For example, the common emitter results in 180 degree phase change. I'll put a link at the top there to a circuit where you can see that happening on a previous video. And also in the world of valves, the cathodine or the long tail pair method of obtaining both an in phase and an out of phase signal are also quite common. You find plenty of those examples in valve guitar amplifiers. Exactly why we want to change the phase we'll look at a little bit later on. So now let's have a look at a transformer of the type that you can see at the top there on the bench and also on the oscilloscope. Okay, here's the arrangement for looking at the impact of a transformer as we've just seen on the slide just now. This is the transformer using, it's just one I've recovered from a switch mode power supply. So I've got the sine wave is being fed in here, and that's currently being displayed on the yellow trace on the scope, as you can see. And the output here I've got attached to the purple trace. I'm now going to connect up that side, and I've wired them so that we should have spot to spot. So I'd expect to see an in-phase signal here. And there's the results, and as you can see at the bottom there, phase difference between 1 and 2 is hovering around the 0, and the waves do indeed look to be in synchro. So that's exactly as we would expect. So that's being transferred across the transformer in phase. Let's now swap over those two wires. So we'll put the red there where the ground was, and we'll put the ground there, and straight away we've got exactly the same wave shape, but as you can see now it's 180 degrees out of phase. So we've succeeded in inverting the phase. So that's the impact that your single winding transformer will have on the phase of a wave as applied to it. Okay, well that's a straightforward transformer with just one winding each side of the circuit. Now let's have a look at transformers that have a centre tap and see what impact that has on phase. Okay, this time we're going to look at a transformer that has a conventional winding on the left and a centre tapped winding on the right. We're going to feed in that same 1 kHz signal, and we hopefully, if we've got I've not put the black dots on here, but if I had, they'd both be at the top. We're going to get an in-phase signal between the top connection and the centre tap, and we should get a signal which is 180 degrees out of phase between the centre tap and the bottom signal. Now that is sometimes referred to as 3-phase. That's because there's also a phase between the top and the bottom connectors, but again we won't go into the detail of that today. But it's incredibly common. Examples of that 3-line transmission include electricity distribution. Next time you drive past a pylon, you may have already noticed they quite often have 3 wires on, sometimes 3 each side. Often on the larger ones there's also a 7th wire along the top. That's actually more to do with earth and lightning strikes than it is to do with electricity transmission. The beauty of a 3-phase electricity transmission is you don't need a return. You can effectively do that using the 3 phases. Again, that's beyond the scope of today. It's quite handy from a noise cancelling point of view. In particular, balanced line is a really nice example of that. And if you've ever been involved with professional grade microphones that have those connectors on that are called an XLR, they have 3 connectors. There's the screened outer, which in the example of this circuit would be the centre tap, and there's usually a black wire and a red wire, which would be the top and the bottom, and the audio signal is transmitted along the line, and there's effectively a mirror image of the signal on each of the red and the black line. Now, were any interference to be introduced along the length of that transmission line, ordinarily you'd expect that to have the to be in phase with itself on both the top and the bottom line, and when it arrives at the other end, the effect of combining those phases should cancel it out. That's certainly how a balanced line works. And it's quite common to want to change phase of part of your signal to feed what's quite often called a push-pull amplifier stage. And again, if I go to my Russian VEF204, there's a nice example from the circuit here. I've tried to put the phase relationship on for you. So transistor 8 on the left, its output is in phase. It's fed into transformer 1, and the output of transformer 1, which is center tapped, should give us a in-phase signal at the top and an out-of-phase signal at the bottom. Those two signals are fed to the bases of the two transistors, transistor 9 and 10, which are wired as to amplify the positive gain and the negative gain cycles. The collectors of those two transistors are connected at either end of another center trapped transformer with the center grounded, so the two out-of-phase signals should be recombined, and what we should get coming out of the side of transformer 2 on the right is a signal which is in phase, and it should be the same phase as it was when it went in from the output of transistor 8. So there's an example of that. Okay, let's now look at a center tap transformer on the bench. Okay, so we've got the sine wave being fed into the primary winding of this transformer, which has a center tapped secondary. So the yellow trace is the signal going into the primary, and as you can see, the purple and blue trace are what I'm taking off the either side of the center tap on the secondary. The blue trace is in phase with the yellow input trace, and the purple trace is 180 degrees out of phase, so that's exactly as we anticipated on the description on the slide just now. Okay, we've seen the way that a center tap transformer produces 180 degree phase change either side of the center tap. Let's now have a look at the notion of recombining those two phases such that we feed a sine wave in, we get our two out of phase signals, they should be recombined, and we should have the same signal coming out the side of a second center trap transformer. So we'll have a look at that. But we'll also develop the idea a little bit further, because there's another way to combine phases, and that is to use a differential amplifier or an op-amp. So we'll take our phase changed signal from our center tap transformer, and we'll feed the top and the bottom sides into the positive and the negative side of the differential amp. We'll ground the center tap, which gives us also a connection to the ground of the differential amplifier, and then what we should get out of the output of the amplifier is a signal which is in phase with the signal going in. So let's look at both of those arrangements on the bench. Okay, here's the arrangement then for the final look at phase. So we've got a center tap transformer here being driven by the signal, which is the yellow trace. Either side of the center tap on that transformer, we've got the purple and the blue trace, which you can see one of the blue trace is in phase with the input signal, but the purple trace is 180 degrees out. This is a center tapped transformer with a center tap winding. I didn't have two of those, so I've just got these two conventional transformers wired in series. I'm not using what would be the center tap on that side, but I am using the series connection for the center tap on that one. It achieves the same ends exactly. And then finally the green trace I'm now going to connect to the output of the transformer, and as you might expect, if you look at the top of the two measurement items, it's saying that the yellow trace on 1 and the green trace on 4 are, to all intents and purposes, in phase. So we've converted from single phase to 3 phase to back to single phase. And finally, I also mentioned another way to use to convert this 180 degrees out of phase signals back to an in phase signal is to use a differential amplifier. So I've got an op amp here, which is a really easy way of getting hold of a differential amplifier. In fact, this is actually an LM386, which is a low power audio amp, so it's quite punchy in terms of an op amp. So what I'm now going to do is I'm going to transfer the green trace from the output of the transformer to the output of the differential amp. And the first thing to notice is we've got a very large off-scale green trace. Well, not surprisingly, the op amp is amplifying, and because it's quite a powerful audio amp, we're going to need to just back off the volts per division there. And if we now change that, you can see quite a lot of amplification, but if you look at the phase difference between the yellow and the green trace, as per the measurement, it is in fact in phase. So 2 out of phase signals being fed into the plus and minus inputs of the differential amp, and we've got an in phase signal which is in synchro with the signal that went in coming out. Okay, well that's about it for this time in terms of looking at phase and its impact on some discrete components. Hopefully it's made some sense and perhaps enlightens you a little bit. I suspect if you're well into electronics, there's probably not a great deal to learn here, but phase can matter, and we've seen that in some circuit examples, and we've seen that phase can both hinder us, i.e. if we get our hi-fi speakers out of phase it's not so good, but it can also help us in the concept of a balanced line system, which permits some level of noise cancelling to go on. Hope that's been useful. If it has, please click the thumbs up. If not, you can click the thumbs down. Either way, thanks very much for watching, and we'll see you on the next one.